Howdy, everybody. Today, I'm gonna try and make super short, mostly because it's the holidays, and well, partly because it's the holidays, and the other part is I actually didn't find any good. Um, uh, I would have had to implement. What I should say is I would have had to implement the algorithms myself in Rust if I wanted to show them to you, and I don't think I have time to do that today. So it would probably take a couple days for me to like fully study out the algorithms. There's a couple of them I'm particularly interested in, but anyway, we'll get to that. Before we get too far, though, I just want to say again, thank you very much. It's awesome to to already see the community growing, and I love getting your input. I've got a lot of things that you guys have mentioned. Hey, you could do this or do that, and or could you talk about this? And I plan on doing that. And today's one of those days, right? Is I think the graph theory stuff is very interesting, and that's what this one was. And so I had a lot of fun doing it or studying, I guess, studying about it. It kind of reminded me of some of the algorithms courses that I went through. Anyway, given that, let's just talk about it. And I'll try and make it really short, and we can all enjoy our holidays. And then I've got some free time that I'll just keep making videos with some of the things you guys had asked about, including let's actually implement the algorithms that we use today in Rust, because I just used an existing library to solve it for us. But here's the problem: it's called Snowverland, and the idea is the snow's still not falling. All this work that you've done, and what you do is you get to this like building, and there's just wiring and stuff all over the place connected to all these different devices, and you come to like the communication module that's like communicating with all these things, and it says error 2023. And basically the issue is there's not enough power. It says you need 100 stars, and of course we only have 49 or 50, right? And so you've got to find a way to reduce the power consumption of all these devices that are wired together. So you're going to get a wiring diagram, which is this. And notably here somewhere in the code, or in the problem, it says connections aren't directional. So what's that's telling you is JQT, even though it's attached to NVD, in both directions is the way to say it. So even though you look down here and see NVD, there's no JQT here. You need to infer from this that this is connected to this way, but also this way is connected to this way. What it's saying is it's an undirected graph, right? There's no directionality to the graph. And many of the things that we've worked on have been directional graphs, right? Is like you're going down a path and you only go one way. And so this one is slightly different, but that should give you a hint of what's going on, right? Okay, I've got an unconnected graph. And then what it says is you've got to reduce the power. Can you find exactly 3 wires that you could cut that would, yeah, it's right here. You only have time to disconnect 3 wires. So can you find the 3 wires that you disconnect, and it reduces the power usage, right? It cuts the power by 50% or more. And so they give you an example here. They say, hey, if you disconnect these 3 wires from this graph that I just gave you, it creates 2 separate disconnected groups of components. And that's like a keyword, if you've heard it before, bipartite graph in computer science. The idea is a bipartite graph is like 2 sets of nodes called disjoint, meaning that they can all talk to each other within these groups, but none can cross, right? And so it's saying, can you find exactly 3 nodes to cut to create this bipartite graph? And if you know a lot about graph theory, or if you don't, I honestly think that if you Googled this, you could find one of these algorithms and probably find an implementation. Again, I couldn't find a good one in Rust. It might be fun to like look at graphing libraries in Rust and seeing if we could either help them with them and to get some of these algorithms in there, or just create our own. So that'll be something to look at in the future. But the general idea is, I honestly think if you Google for it, because you would say, like, for example, your Google might be, what are the minimum number of cuts I can create in a graph to put it into two separate groups or whatever, right? And boom, it would pop up with Edmonds Carp or Ford Fulkerson. This is like, it would, these ones would be like the maximal flow is equal to the minimum cuts, right? And I can show you really quick. Or you might come to Stoyer Wagner. This one's actually more closely related to the solution because it's an undirected graph. It does use weights in the graph, so you can see it's a weighted edge. But in our case, we can just assume the weights are all 1 and solve it with this one. But let's talk about why this is important, and maybe pique your interest for when we come back and actually implement these algorithms. So here's the graph that they give you, the wiring diagram or whatever. And if you notice, if you look close enough, you can kind of see there's kind of like two groups that have formed. And if you cut these 3 lines right here, it completely separates the groups, right? And why is that important in graph theory? Well, you can think about these 3 nodes as like the critical paths of the graph, right? So any traffic or anything that's wanting to go from this side to this side has to use this, right? And there's 2 ways to think about it. One is like, you know, for example, a highway or something like that, right? You have a bunch of interconnected highways. If you're worried about making sure that all of these, you know, towns or whatever can connect and work with these towns and there's commerce between them, you need to make sure that these are always up and running, right? So these ones have like the most effect on that, right? Or like in this example, a minimal cut, like what is the corollary to like the minimal cut is like, if you're trying to find like a way to be least disruptive of the network, but separate the groups, that's what you'd want to do, right? The Ford Fulkerson has to do with it. In fact, if you ask it, it computes the maximal flow of the flow network. So it assumes that it's a flow network, but we can turn our graph into a flow network relatively easy. Ours is undirected, flows are directed, so you'd have to like, you'd now say, oh, there's a link from here to here, and there's a link from here to here, and that is directed, which we kind of we already have to do anyway. But and then you just have to give these like capacities of flow, like how much traffic or how much electricity or water can flow between them. And again, if you default it to 1, you can solve it. But based on that, you can do the maximal flow, right? And maybe I should say the way to think about the maximal flow is, if you're starting here and you're wanting to end here and you want like you're spitting out a bunch of water right here and you want to know how much, what's the maximum amount I can put over here. And these all have different weights, right? Or different capacities is what we'd use for a flow graph. Yeah, and so like maybe this one you can send 5 here and you can send 7 here and 10 here. And like you start doing all this work, and what you notice is like this one and this one and this one have like the most effect on the maximal flow. Like these 3 lines right here are the 3 pieces that that have the most effect on getting water or whatever from here over to here. And so what you'll often hear if you've taken these classes or start watching some other videos is the maximum flow is the minimum cut. They're the same thing. They're asking the same question, and the general question they're actually asking is like, what are the critical points in the graph, and that kind of make it that if you cut them would make them a bipartite, or are severely restricting the flow from this side of the graph to this side of the graph. But you know, so they're just different ways of implementing this notion of, can you find these like very critical points in the graph? And so they have lots of useful purposes, again, for flow graphs and stuff like that, those type of things, right? So how do you solve this? Well, obviously it would be fun to implement one of these algorithms, and I plan to do that, right? Especially this Steuer-Wagner, I started working on it, but I just ran out of time because it's the holidays and I need more time to work on it. It doesn't look like it's much, but there's a lot to this, right? Like the most tightly connected vertex, that's, you're doing like a breadth first search there, right? And so these are things that like we will have to implement. It'll probably, my guess is it's around 100 to 150 lines of code. And so, but I want to implement this one. The maximal flow one I think is good. We can try and implement some of these and look at them. But once you know that these are the solutions, you can just, I did it in Python today, mostly because I couldn't find them in Rust. There's not, like, for example, this networks library, there's not a lot of other, equivalent libraries in Rust, at least that I could find. So if you know any of them, I would definitely like to hear about them and maybe even help contribute, right? Some of these graph algorithms are not like impossible to implement, right? If you know things about like min heaps and, finding neighbors like edges and vertexes and stuff like that, they're not that tough to implement. And so, my plan is to show you how to do that in Rust. And so maybe we can even do it with someone else's thing. But the idea was, it's December 25th and I don't want to spend a bunch of time doing that. We'll save it for another video. Here's how you would do it, right? Given those algorithms. First, I need to create the graph, and then I need to add my nodes to the graph. And notice again, like as I'm going through the list, I add it in both directions, right? This capacity is necessary for the minimum cut solution. This one down here, again, because I think it uses, you can tell I'm tired from being Santa's helper, putting all the stuff together for Christmas. But the idea is you need the capacities for the flows to solve it, right? But you can see here is I literally just, once I've created the graph, I can run the Steuer-Wagner algorithm, and the I hope I'm saying Steuer's name right. I think it's Steuer. Or otherwise I can do the minimum cut. And you can see this one's pretty slow. It does have a higher complexity because, like, even if you implement it with a min heap, it's still like the number of edges squared. Sorry, I think it's like the number of vertices squared plus the log of the number of edges or something like that. In the best case, right? If you do it in the best case, it's still pretty poor. So it's pretty slow. The min cut one is faster, but it's mostly because in this case, the min cut, I mean, I think it does apply to what we're trying to do here. So I don't want to give you the impression that it doesn't, but you have to go about solving it in a funny way. Basically, in order to find the minimum cut or the maximum flow, you need to have a source and a sink. You need to have like a start and an end for the flow, the directionality of the flow. And that will not work if you pick the wrong source and sinks, right? So when you're looking at this graph here, like you kind of have, because you don't know ahead of time that this one's on this side and this one's on this side, it may not immediately find these cuts, right? It will, like, for example, if the first ones you pick are this one and this one, well, it might just say, oh, if I just cut right here, then I've solved that problem, right? That fixes it or whatever, right? So what you do is you go through all the nodes, like create the cross product of the node, not the cross product, the Cartesian product of all the nodes. You try all of them with all of the other ones, and if you ever get to a point where you've partitioned it and it took exactly 3 cuts to partition it, again, to create that bipartite graph. That's what it's saying. Once you've done that, then you've solved the problem. And so if you get lucky and you only have to check like the first few, super fast. Whereas with the Steuer-Wagner, it's got to do an analysis of the whole graph, excuse me, to find it, right? And so that's why this one takes substantially longer than this one, because this one is like you're kind of short-circuiting, but you're doing it in kind of a, I don't know. It's not really cheesy, because what you just need to do is eventually you will find one that's on this side and on this side, and then it will produce these three for you. So anyway, that was it for day 25. Again, there's not a lot to it. There's some fun graph theory things that I'd love to talk about more, but there's not really an algorithm to go over. I don't want to get into too much details of the Steuer-Wagner or the minimum cuts, because they well, I describe them at a high level, and I think you can, make sense of it from there, but actually implementing it is going to take some time, right? So it'll be several hours on my part, and I didn't want to do that over the holidays. So there you go. There's day 25. One last time, thank you for watching these 25 videos of Advent of Code. I really appreciated all of your feedback and all the interesting things you said. I've been keeping notes of the things that I want to go over and talk about from these days, but also all the input that you all have given. I've written all that stuff down, and some of them I've even started to make changes on, and I'll just keep making videos that talk about all of those things. So, and hopefully you find those things interesting. So there you go. It was, this is kind of it felt like maybe a downer of a day compared to the other days, because it's really just, I'm going to run this algorithm. But I imagine, unless you know how to implement these ones yourself, there's probably not much to it. And in fact, I bet if I'll go watch some videos after the fact, but if there's other people that do these kind of videos like I do, I like to watch some of the people who try and solve it as quickly as possible. Almost assuredly, they probably just use this thing. In fact, we should go look at the leaderboard for the day and see how fast these were solved. Yeah, like these ones, 2, 3, 4 minutes. They almost certainly said, oh, I can just use the minimum cut thing, or I can use this, and that's how they were able to solve it so quickly. Maybe they didn't, but I would be highly surprised if they didn't. So there you go. And there's the end. Maybe one of these years I'll try and get high on the list. I think this is the guy I watch sometimes on YouTube. Maybe next year we'll stay up late and try and solve them as quick as we can. I am not fast, so that's why I don't usually do it. Most that just maybe is like here's Advent of Code. I enjoy Advent of Code because it helps remind me of some of the cool things that I learned about, or it teaches me something new, right? Like, I think we went to the 25 days and I kind of had an idea of what most of them were, but that's mostly just because I've been doing it for a while. I've been trying to solve these problems for a while. I find these problems fun to solve. So, but there were a few I didn't know, and that excitement of either solving it yourself and then going and looking and saying, oh, I figured out, network contraction on my own, or whatever, right? Those type of things. Maybe you didn't implement it the most efficient way, but you kind of saw the problem and could visualize it and make it, or you learned something you'd never known before. I actually had not heard about the Steuer-Wagner algorithm, even though I was, I was definitely around for all of this, but I had heard of the maximum flow thing. And so that's what kind of led me to the thing. But learning these new tools like this algorithm is kind of fun. And so that's why I want to implement this in Rust, right? So that's why I love Advent of Code. And that's why I hope you'll keep watching these videos if you're interested, because I just want to share that excitement, right? And so if you have something that's exciting that you want to share, feel free to send it to me, and or you have something that you want to understand, maybe I can help you, get excited about that. Anything computer science, computer engineering, computer related, right? Those are the things I'm super interested in. Obviously, a lot of you have asked about Linux and stuff like that. I'm a big fan of Linux. Been using it most of my adult life, except for when I have to boot into Windows to play video games with my children. But that, those I love technology, right? As they say in Napoleon Dynamite. I'd sing the song, but I would lose subscribers. I'm almost positive if I started singing. So there you go. That is the end of the Advent of Code. I had a lot of fun, and it was great to communicate with you all to get new ideas and new things to do. And we'll plan on doing them in the future. So talk to you later.